It's important to note that r and theta do not care what the z-coordinate is. So let's draw the graph of r is equal to 2 in cylindrical coordinates. So r equals 2, we had already drawn what that looks like in polar, but that was a two-dimensional picture. Now, if we are being told in the question that this is in cylindrical coordinates, that means we are already in a three-dimensional space. Okay, so x-axis, y-axis, z-axis like this, and that means that there's a circle down here of radius 2, but that's just in the xy plane, and then there's another copy of that same circle above and above and above and so on. And so what that ends up creating is this infinite tube. This tube just keeps on going upwards and downwards. Okay, this is like a sort of like an infinite, in that you can go infinitely up or infinitely down. Paper towel tube. Okay, I'd like to ask you to take a moment to draw r equals 0 in cylindrical coordinates. So perhaps pause the video, try this on your own. Okay, so what should the picture of this be? If it's r is equal to 0, now just on the xy plane you just get that one point. Then all along the z-axis you get, well, all these points. So what you end up getting really is just the z-axis in its entirety. Okay. The reason to make sure to really understand this one is that it is meant to help clear up the idea that r equals 0 is not about the distance that the point is away from the origin in its entirety. It's just the distance in the xy plane. So the z-coordinate is independent of what's going on with r. Okay, let's draw theta equals pi over 4 in cylindrical coordinates. Now we already did this theta equals pi over 4 in polar coordinates, but in cylindrical coordinates, let's think about what this has to be. X-axis, y-axis, z-axis. Well, we had earlier this line right here. If this angle was pi over 4, and this line continues back here, back this way, and we actually have then, remember theta is also independent of z, so we actually have above this line another copy of this line, and so on. So we actually have a stacked copy of lines on top of each other. This is going to end up becoming a plane. Right? So this is a plane. And specifically, because the angle pi over 4 is so nice, we can actually maybe mention just exactly what equation this is. This is the plane. X is equal to y in sort of our standard Cartesian coordinates, in Cartesian or rectangular coordinates. Okay, let's try to make sure we understand what's happening by doing another. Let's draw theta is equal to 3 pi over 4 in cylindrical coordinates. Again, if we just said draw theta equals 3 pi over 4, it could have been confusing whether this should be in polar coordinates or cylindrical coordinates. If it were in polar coordinates, we'd only draw a 2D picture. And so let's draw the 3D picture that we should have here. It's x-axis, y-axis, z-axis. So there's 3 pi over 4 should be right over here. So there's this line back this way, and of course because r can be negative, this comes back this way, and then we have this plane that looks like this, and of course it goes downward as well. I think this is a good time to just note, or just notice, that if you have theta is equal to a constant, in cylindrical coordinates, this is a plane containing the z-axis. So maybe think of, and I'll switch to degree mode here for a second because I think it'll be a little easier to describe. Think of theta equals 60 degrees, and then the graph of theta is equal to 61 degrees, and the graph of theta is equal to 62 degrees, and so on, as a, I don't know, like a rotating door. Okay, let's draw z equals 3, again in cylindrical coordinates. Okay, remember that the value of r and theta are independent of z. So z equals 3, it's really just this plane, a plane that's, you know, completely horizontal. It's parallel to the xy plane that just contains this point here. Right, so this all points, it's the plane where all points in this plane have z coordinate being 3. And this is actually the same, z equals 3 in Cartesian coordinates. So that hasn't changed. Okay, let's try another one. Let's try drawing. We've got to just get used to this coordinate system before we talk about integration. So let's draw z is equal to r. Okay, remember r is just the distance with respect to the xy plane only. So what we end up actually getting from this is the shape is going to be a cone. I'll try to draw this as best as I can. X, Y, Z. So however far apart, so let me just try to draw in the xy plane itself. This is really, it's challenging to try to, so like all these, let's just draw a circle, I don't know, just of radius 2 for a second, right? All of these points have the value r is equal to 2, and those points should not be drawn here in the xy plane, but rather 2 units higher, because that's where z, you know, z should equal whatever the r value is. So in doing so, you end up actually with just a cone that looks like this. So for instance, I mean, let me just try to sort of back do this here. Like, let's just say that this is where z is equal to 8. That's because back here, if we just look at what's going on down here, this circle over here, if we were to draw it down here, we really shouldn't. It's not this circle that I'm drawing dotted down here isn't really part of the picture. But if we understand what circle that is, that's a circle itself of radius 8. All of these line segments should have length 8.